Analyze the given continuous beam by flexibility method. Support B sinks by 5 millimeter. Consider EI equals 15 into 10 to the power of 3 kilonewton meter square. Here A to B. A is fixed support, B is on hinge and is subjected to a load of 30 kilonewton per running meter with moment of inertia 2I and the total span is 6 meter. B to C, it is 4 meter. C is the end support which is on hinge and is subjected to 120 kilonewton load at a distance of 2 meter from B with moment of inertia I. First you have to find out the degree of redundancy. The degree of redundancy is given by number of unknowns. Here at support A, fixed support A, MA and VA are the unknown reactions. Here no horizontal forces, hence not considered HA. Then at support B, either VB or MB you have to consider. At C, that is the end support which is on hinge, VC is the only one reaction component. Then the total number of unknowns are 4. The number of available equations of equilibrium are: one is summation of Fy, another Fy equals 0, and another one is summation of Ma equals 0. We have not considered summation of Fx equals 0 since it is not subjected to any horizontal loads. Hence, the degree of redundancy is number of unknowns minus number of available equations of equilibrium. That is 4 minus 2. Hence, degree of redundancy is 2. Here, we can consider the reaction, support reaction VB and VC as the redundants. Here, the redundant matrix R is given by VB and VC as shown in, as given in the table. The next step is we have to remove the redundant reactions and made it basic determinate structure. Here we have removed the redundant. In place of redundant we have given the coordinates. This one is first coordinate, this one is the second coordinate. Here now it is free. This one is subjected to load, it will undergo deformation. Here the displacement due to the loads at coordinate 1 and 2, that we have to calculate. Here there are two different loads are acting in A to B. This one is A, this one is B. Here that is subjected to UDL. A to B it is subjected to UDL, and B to C it is subjected to point load of 120 kilonewton. First we have to draw the bending moment diagram, then M by EI diagram by using the moment area method. Here this is the bending moment diagram due to UDL. By the principle of superposition we have to superpose the two bending moment or M by EI diagrams. Here to get the displacement at 1 due to the load, applied load in the direction of the redundant one at coordinate 1. Here this is the bending moment is 30 into 6 into 3. Here the moment of inertia is 2I. Hence the M by EI diagram, that is the ordinate of the M by EI diagram is 270 by EI. Then here this one is 120 into 2, this one is 240 by EI is the M by EI for this span between B and the point load. This one is M by EI diagram. Here similarly, here the bending moment is 120 into 8, that one is 960 by 2 EI, that equals 480 by EI. Similarly here there are two ordinates, one is 240 by EI, then here the moment of inertia changes, hence there is another ordinate, that is 120 by EI. First we have to calculate the displacement at 1 due to the applied load by taking by the moment area method moment of the area about the point number 1 in between A and B give us the displacement in the direction of the displacement at coordinate 1 to 2, the applied load. Here this one is 1 by 3 base 1/3 of base width into ordinate which is acting at a distance of 3 by 4 times 6 meter. Then here this is as shown in figure. Similarly for this one, here this portion, that is half into half into here this portion, that is half into 6 into 120 by ei, 120 by ei, this triangle, this is second triangle, this one is into centroidal distance is 6 by 3. Similarly this one we have split this into two rectangles. This trapezium is divided into two triangles. This one is one triangle, this one is another triangle. Similarly the displacement due to this one is half into 6, half of the base width into ordinate 480 by ei into centroidal distance is 2/3 of 6. By simplification you will get the displacement at 1 due to the applied load as, that is after simplification here you will get 8910 by ei, 8910 by ei. Then delta L2 equals displacement at 2 due to the applied load. Here by the second moment area theorem, that is moment of the total area between the point under consideration and here between A and C about C, that is here first consider due to UDL, that is 1/3 of span into ordinate is 270 by ei into the centroidal distance is 3/4 of 6 plus 4 meter, the distance between centroid and the coordinate 2. Then similarly for this triangle, that is half into 6 into ordinate is 120 by ei and the centroidal distance is 6 by 3 into 6 by 3 plus 4. Then third triangle, that is the third one, that is half into base width is 6 meter, ordinate is 480 by ei into centroidal distance is 2/3 of 6 plus 4. Then this triangle, here half into base width is 2 meter into ordinate is 240 by ei and the centroidal distance is 2/3 of 2 plus 2. Then after simplification here you will get 19,070 by ei. Here the displacement matrix due to the applied loads is given by delta L1, delta L2 are the elements. Here 1 by ei is common. The elements are 8,910 and 19,070. Then here the support B sinks by an amount of 5 millimeter. Here this one with respect to A, this is A, this one is A, this one is B, this one is C. Here delta A is 0, delta C is 0, but delta B is 0.005. Here we have to convert that into meters. Then the displacement due to sinking of the support is given by delta 1 at delta 2. Here at coordinate 1 there is a sinking of the support by an amount of 0.005 in downward direction, and delta 2, that is at support C, there is no settlement, hence that is 0. Then here by removing the applied loads in the direction of the redundance, in place of the redundance we can apply the unit load. We can assume the direction of the reactions. Here at 1 we have applied a unit load in the direction of the redundant. Here this one is R1. In place of R1 we have applied 1 kilonewton, and by drawing the bending moment diagram, here the ordinate of bending moment diagram is 1 into 6, that is 1 into 6 divided by moment of inertia is 2i, hence that is 1 into 6 divided by 2ei, that is 3 by ei. Here F11, the flexibility element at 1 or the displacement at 1 due to the unit load applied at 1 is given by m by moment of m by a diagram between this point and this point, that is f11 equals half of the base width is 6 into ordinate 3 by ei into centroidal distance, that is 2/3 of 6, that one is 4 meter. Then after simplification f11 equals 36 by ei. Similarly, f21 displacement at 2 due to the load applied at 1, that is the moment of this area about point or coordinate 2, that is given by half of base width is 6, ordinate is 3 by ei into centroidal distance is 2/3 of 6 plus 4, that one is after simplification here you will get 72 by ei. Then here now we have got the values of the flexibility elements at coordinates 1 and 2. Now we can apply the unit load at coordinate 2, unit load in the direction of the redundant R2, that is now this one is the flexibility element F22 at this point, that is F12, that is displacement at 2 due to the load applied at 2, displacement at 1 due to the load applied at 2. Here by applying the unit load, first you have to draw the bending moment diagram. Here there is a variation of the moment of inertia. In this portion the moment of inertia is I, in this portion A to B the moment of inertia is 2I. Here after knowing the bending moment, that is 1 into 4 divided by ei, this one is m by ei diagram between B and C, this is the centroid. Then here the bending moment is at A, 1 into 10 divided by 2 ei. This is the ordinate of m by ei diagram, that is 5 by ei. At this point at B, there is moment of inertia changes from 1 ei to 2 ei, hence here again we will get one more ordinate, that is 4 divided by 2 ei, that equals 2 by ei. Here this ordinate, that is 1 over 2 over ei. Then the displacement at 2 due to the load applied at 2, that is given by the moment of the total area between A and B, A and C about C or about coordinate 2, that one is F22 equals, here this one is, first we have to calculate half of the base width into 5 by ei, this triangle the centroidal distance is 2/3 of 6 plus 4, that is 4 plus 4, that one is here I have written. Then for this triangle, this one is the trapezium, we have divided this trapezium into two parts or two triangles. Here for this triangle half of base width is half of 6 into ordinate is 2 by ei into centroidal distance is 1/3 of 6 plus 4, that is 2 plus 4. Then for this triangle, that is half of base width is 4 meter into centroidal distance is 2/3 of 4, 2/3 of 4, the ordinate is 4 over ei. Then after simplification here you will get 532 by 3 ei. Then F12 displacement at 1 due to the load applied at 2, here that one is given by half of 6, half of base width into height ordinate into centroidal distance 2/3 of 4, only in this portion that we have to calculate the displacement at with respect to the tangent drawn at A, the deflection at coordinate 1, that is m by moment of m by a diagram between A and B, that one is here again this one is half of base width into half of 6 into ordinate is 2 by ei, and the centroidal distance is 1/3 of 6, that is 2. Then that one is this one is the centroidal distance 1/3 of 6, that is 2. Then after simplification here you will get 72 by ei. The flexibility matrix F is given by F11, F12, F21, F22. Here, this one is 36 by EI, 72 by EI, 72 by EI, then 532 by 3 EI. The final redundant reactions are given by R equals, we know that R equals the redundant matrix is given by inverse of the flexibility matrix into the displacement due to the sinking of the support, displacement vector due to sinking and settlement of the support minus the displacement due to the external applied loads. Then by substituting the values, that is R1, R2 are the redundant reaction, that one is R1 is the support reaction at B, R2 is the support reaction at C, that one is inverse of flexibility matrix. The elements are 36 by EI, 72 by EI, 72 by EI, 532 by 3, and the displacement vector said due to the settlement. Here settlement at support or at coordinate 1 is 0.005 and the settlement at 2 is 0 and displacement at 1 due to the load is minus 8910 by EI. Similarly at 2, that is 19,070 by EI. Then here after calculation of this, after simplification, here we will get the reactions R1 and R2, that is the redundant reaction is given by R, the redundants are given by R1 equals 161, R1 equals 161.42 kilonewton. That is, we have considered the support reactions as the redundants. R1 is the support reaction at B, then R2 is 42 kilonewton, that is the reaction component, vertical reaction component at the end support C. Then here by using this we can calculate the bending moment, we can draw the bending moments diagram, shear force diagram and the elastic curve. Now we can draw, we are able to draw the bending moment, shear force and shear force diagram and elastic curve. Here the first we have to draw this. Here we have already calculated the redundant reactions VB and VC. VB is 161.42 kilonewton, VC is 42 kilonewton. By applying the equilibrium equation, that is summation of Fy equals 0, by using that we can calculate the support reaction at A. Va equals, that is 30 into 6, this one is downward, that is, and 120 point load, that is 120 in downward direction. Here the support reactions VB and VC are 161.42 and 42. Just now we have calculated by applying the equilibrium equation summation of Fy equals 0. Here we will get the support reaction at A, Va as 96.58 kilonewton meter. Now by using that we can easily draw the shear force diagram. Here the variation of the shear force, here this is Va, this one is left upward is positive, then left upward the shear force variation is like this. Here this is 0 to 96.58. Here draw this ordinate, draw this that is the bottom line or reference line. Here at A, 96.58 is the shear force, that is upward, that is positive, left upward is positive, then 96.58 show in upward direction. Here the shear force gradually decreases since it is subjected to a UDL of 30 kilonewton per running meter. This one is the variation of the shear force is 96.58 minus 30 into 6, that one is 83.42. Here the variation is a straight line like this. Here there is a support reaction of Vb equals 161.42 minus 83.42 plus 161.48. Here you will get the ordinate of the shear force as, that is 78.00 kilonewton. In between this point and this point, no loads are acting, hence the shear force remains constant, that is plus 78 kilonewton. Then because of this point load, that is minus 120, 78 minus 120, here you will get 42 kilonewton, that is negative shear force. Then here, because of this reaction at Vc, then minus 42 plus 42, the shear force becomes finally it is 0. This one is here, this is A, this one is C. At A and C, the shear forces are 0. Here, this is the shear force diagram. This is positive, this is the positive shear force diagram. The shaded portion shows the shear force variation diagram from A to C. Then here, by taking the moments of all the forces about B to the RHS to calculate this moment, that is 42 into 4, 42 into 4, that is anticlockwise, 120 into 2, that is clockwise. Here we have assumed MB as anti-clockwise the moment, hence MB equals 72 kilonewton meter. That is hogging moment or the bending moment is anti-clockwise. This one is hogging. Similarly, this one is also same. Then summation of MA equals 0 by using that Vc into 10, that is 42 into 10, that is anti-clockwise. Then 120 into 8, that is clockwise. Then 80 into this one is 30 into 6, which is acting at a distance of 3 meter, that is 30 into 6 into 3, that one equals, and then minus here due to this one 161.42, just now we have calculated by applying the by the one of the redundant, that is VB into 6, then that is 161.42 into 6. Therefore, MC equals 111.48 kilonewton meter. That is also a hogging moment or that is anti-clockwise moment. Here, the support moments are 111.48 and 72 kilonewton meter respectively. To draw the bending moment diagram, first we have to draw this reference line or the datum line. Here, the moment, this support moment is hogging, hence we have to draw the ordinate above the reference line. Similarly, here the hogging moment, hence we have to draw the ordinate of 72 kilonewton meter. Join these 2 points by a straight line. Here the variation is straight line. This bending moment, that is negative bending moment. Then here the bending moment at C is 72 kilonewton meter, that is hogging, and then at support C, that is 0. Here we have to overlap the simply supported beam bending moment diagram over the support moment diagram. Then here in this portion A to B, that is subjected to UDL of 30 kilonewton per running meter. Then the maximum bending moment occurs at the center. That one is given by WL square divided by 8. That one is W is 30, L is 6. Then that equals, after simplification, here you will get the bending moment of 135 kilonewton, which occurs at the center. Then here at support it is 0, that is curve like this. Here by overlapping, the net bending moment is given by the shaded portion as shown in figure. Similarly, in portion B to C, it is subjected to a point load of 120 kilonewton. The maximum bending moment occurs below the point load, that is acting at the center, that is WL by 4. 120 into 4 by 4, that is 120 kilonewton meter. At the below the point load, at the support, the bending moments are 0. By overlapping, you will get, and by showing the shaded portion, we will get the net bending moment in the B. This one is the shear force diagram, and this one is the bending moment diagram for the given problem. Okay, we will continue in the next video.